Thanks so much for inviting me first. I'm thrilled to be here. Actually, I just realized while sitting here that the first talk I gave was 10 years ago at a conference in St. Petersburg. And actually, funnily enough, Sergey was the one who organized that conference. So thank you. Yeah, my name is Anton Bikineev. I work on Chrome here at Google. Not here in Zurich, but in Munich, as Sergey mentioned. Yeah, the talk will be more specific. The talk will be about how we optimized Chrome within the last year. Right. I'm going to just tell the story of this. And I also hope maybe the main goal for me would be that you could learn something from our experience. That would be really great. I also must say that before we start that I'm not a performance or hardware expert. I'm just a guy. I'm not even a C++ expert because I don't know all the ways to initialize the object in C++. Yeah, so this year was a huge sprint, as I've said, for us to optimize the browser performance. Only within the first quarter, we shipped a bunch of optimizations that made the browser 10 to 15% faster on various benchmarks. Yeah, the slide shows what the press wrote about us. I'm really proud of all the work the entire Chrome team has done to contribute to the success of the browser. Right. So what won't be covered on this talk is basically macro optimizations. Like we shipped a new JavaScript compiler. I actually work on the V8 team, and we shipped a new JavaScript compiler, a new tier, basically. We now have 4 tiers, compilation tiers. This doesn't have much to do with C++, so that's why I'm not going to cover this. We also have some user optimizations like back forward cache, page preloading. This is just like the user experience optimization, so I'm not going to cover this. Right, so, but before we start optimizing anything, we must be able to measure what we optimized. So there must be some metric, right? And this metric must be representative of the user workloads. For our case, we use the Speedometer 2 browser benchmark. This is probably the most famous one. There will be another Speedometer 3 next year released. So this is what usually the browser used to compare themselves. So the benchmark looks like this. So basically, it manipulates with DOM using different JS frameworks. So it basically adds to-do entries to the DOM, then deletes them. DOM manipulation, basically. So, and the stories, the frameworks we are going to cover mostly will be jQuery and Vanilla.js because they go to C++ more often. They manipulate with DOM more often. Yeah. So, yeah, let's start with the basics. Optimization flags. That seems obvious, I guess, for everybody. I hope I'm not bored. I'm not boring for you now. But yeah, there was a true story, a project I worked on many years ago. It was a Java project, but there was some tiny part written in C++, and we expected this part to be really, really hot. And it actually turned out that it was not as hot enough, and we thought okay, Java probably is already fast enough, and this is comparable to to C++. Until one day when somebody found out that the C++ code was built without optimization flags, and the reason was the project used Maven, the Java build system, and there was a CMake plugin for this build system, and nobody cared about the default build type, CMake build type being debug. So one day it was 10x faster, and yeah, that's a true story. I'm not gonna say what company it was, of course. Yeah, so link time parameterizations, they are extremely useful. They enable whole program analysis. They enable optimizations across different translation units. They give significant runtime gain at the cost of slower link time. Yeah, profile guided optimizations. They are great. They give significant gain. I believe it was about 17% on speedometer when we enabled PGO on Chrome. And the cost is basically a lot of extra work in the pipeline, right? You need to have 2 binaries, one for collecting profile, and you need to collect the profile, and then you need to have another binary that consume this profile. Yeah, there are different approaches of generating profile, instrumentation-based one and sampling-based one. We used instrumentation-based one, but which one to choose is basically out of the scope of this talk. Yeah, and there's also an advanced topic, posting time optimizers, like the binary optimizers. So there is one called Bolt that was developed by Facebook and that was upstreamed to LLVM. So yeah, this is a nice thing that actually performs optimizations on the binary level. On the binary level, it doesn't need any source code information. I believe even it doesn't even need the debug symbols. So it's great for generating optimal code layout so that your code doesn't suffer from like ITLB or iCache misses. Right. So I believe that we have Clang build optimized with Bolt so that our builds become faster, and it got 4% faster build, Chrome build on Linux. Yeah. Right. So when it comes to profiling, there is this famous phenomenon called developers' bad optimization intuition. Yeah, in my own experience, it often holds, but not always, because intuition is still based on experience. But since our field is rapidly changing and actually quite complicated, and the hardware advances too fast, this experience gets quickly invalidated. So hence, we have this phenomenon. So therefore, use the profiler. And I claim that profiling infrastructure must be as easily accessible as possible to developers. Yeah, if your project cares about performance. And the developers must be comfortable with the profiler, as comfortable. The same story goes for the debugger. We use, for profiling, we use Linux perf, the sampling profiler, and we use pprof to visualize the profiles. We do love flame graphs. So flame graphs, basically, very simply speaking, is just a collection of stack traces sorted by the most expensive ones to least expensive ones. So this is just an example. You probably cannot hear much from this graph, but it doesn't matter. So yeah, so then the very first question was what to profile. And the easiest thing to look is the bottom-up view. The view gives you basically the inverted call tree where the parent is the callee and the children are the callers. However, the profiler usually doesn't give you all the leaf functions. It gives you the list of all the functions sorted by the self-time, where self-time is the time taken by execution of all instructions in the functions, excluding all the callees. So it's really helpful to identify some program bottlenecks and apply micro optimizations. And of course, what we can see from this is allocation functions. So in Chrome, we use partition alloc allocator. And so these are just the symbols for malloc and free. And we see that they can actually take significant amount of cycles. Right, so allocations. Yeah, we are C++ developers. We know that allocations are a slow thing. So if you look at all the colors of the malloc on the vanilla JS story, we will actually see that it's probably not clear here, but 50% of the cycles actually coming from the allocations of some class hierarchy, interpolable number, list, whatsoever. So if you look closer at class hierarchies in C++, it's quite typical, right? We have it everywhere. We all love the Gang of 4 book on design patterns, right? So we have the composite object here, the list. But in C++, having a class hierarchy means that we usually operate with reference semantics, and reference semantics usually means that we have allocations everywhere. Otherwise, we have like scoping issues and whatsoever. Right, so there is a nice talk by Sean Parent, Inheritance is the base class of evil. I guess it's like probably the most cited one. I guess the talk was in 2013 or yeah, but I constantly hear people like referring to the talk. So and if you have class hierarchies, basically some of the objects can end up having a non-trivial layout. Like here, for example, there is a color object having a bunch of unique pointers to numbers, has a pointer to the list, which has a vector pointing to the vector bucking, and the vector bucking has a pointers to unique, to number. This is quite a lot, right? This seems like we have 11 allocations for a single color object. The payload of the color object is just 8 doubles, right? It seems like we pay a lot of overhead for allocations, a lot of overhead for out-of-line accesses, a lot of also memory overhead because of pointers, right? Yeah, so the idea was quite simple. We can flatten the object layout like within a single object. So it's all, we have no allocations at all, no indirections. The data is really cache friendly. That seems trivial, yeah, but it violates a lot of like design patterns that we are used to. We cannot dependency injecting into the color object, right? We cannot do it basically. It's not extendable anymore. It's all fixed now. So this is the issue, right? But if we look at the performance, this is what it used to be, the flame graph of the colors of the malloc. And this is what it has become. So we have now 33% fewer malloc cycles, and it improved the speedometer score by 1.5%, which is actually quite a lot. So we are fighting for every single, 0.1, 0.2%, and only like removing these allocations improved. Yeah, at the cost of making the code really not as great. Okay, right. So if we look at what we have actually in C++, we can have reference semantics and value semantics. Yeah, so with reference semantics and class hierarchies, we usually can follow good old object-oriented practices, right? And the code can be extendable, right? We can add new classes, we can add delegates that can forward to the existing classes and so on. But at the same time, we have heap allocations, we have indirections and so on. On the other hand, we have value semantics, right? With something, for example, like std variant or fixed set of things. This enables stack allocations. Because of that, we potentially may have better performance, but the code is not extensible anymore, and the code actually becomes harder to write, in my opinion. It becomes ugly with like std variant, std visit, and so on. I don't really like it, and it can result in a larger memory footprint because every single object you allocate is basically a union, like the maximum. It has the size of the maximal object in the set. So, and the question is, can we have something in the middle? In C++, of course, we can have some automated unboxing. I don't know, I call it so, but the idea is really simple. It's based on type erasure, the same technique that is used for std function or for some other things. Yeah, and based on small buffer optimization. So it's basically a wrapper around a unique pointer with some inline storage. So, right, so, and we have a pointer which either points to inline storage or to out-of-line storage. And whenever you create a concrete object, you check whether the object fits in the inline storage, and you construct it inline. And if it doesn't, you construct it out of line, right? So it's as simple as that. Louis Dion had an excellent talk on runtime polymorphism, and actually I think that Louis has a library that implements it all for you. So we actually tried this approach in Chrome for this specific hierarchy. I tried it, but I haven't seen performance improvement. I believe that this is because I've already optimized the low-hanging fruit, and the rest was just not visible. The rest of improvement. Right, so let's talk about hidden costs of runtime polymorphism in C++. So assume we have a class hierarchy. Sorry. Yeah, assume we have a class hierarchy. And following the Scott Myers advice, if you have a class hierarchy and we have an interface class, we need to provide the virtual destructor, right? Right, but assume that only a tiny fraction of the hierarchy actually have some destruction semantics. This is actually the real case for DOM, for example. And this is what we've seen. And all the rest of the classes, they actually don't need any they don't have any destruction semantics. So, but this is the lowest common denominator if you have an interface class. Yeah, you have to provide the virtual destructor, and then suddenly the entire hierarchy becomes non-trivially destructible. Right, so you have a lot of no-op destructors. For example, if you have to execute a cd vector, clear the vector of such nodes, you would have to deallocate the objects and also call no destructors like multiple times. We actually have seen this in the flame graph as well. I would say that this cost is actually non-trivial and hardly optimizable. Some can argue that actually it can be dominated by the allocation, but not necessarily, right? If you have like fast allocator based on free list, for example, the free list, the allocation would be just 2 memory stores, and on top of it you would have a lot of the virtual table plus indirect call. Yeah, which is the compiler cannot optimize even with PGOs. So right, so we do see the next hidden cost, which C++ developers often tend to forget about, is reference counting. So with class hierarchies, we usually like to use shared pointers, right? We do love them from Boost and C++ 11. We've been using those. Right. However, the cost of them is non-trivial at all. Like if you look closer, it involves out-of-line access every time you construct or destruct shared pointer, right? On decrement, it involves log prefix instructions. Like think of it as exchange, for example, on x86. So, and on decrement as well. And on decrement, it actually has to do the memory barrier because it needs to synchronize whatever the user code has with the destructor of this class. So on weakly ordered instruction sets, you would see the barrier, right? Yeah, this could be tricky. And if you look at the cost of reference counting only on the main thread of Chrome, on the vanilla.js story, it would be 1% of cycles. This is just a whole lot, right? 1% of cycles we spend in the entire program just by doing the reference counting. And if you look at jQuery, it's even over 2%, only on reference counting. I was surprised myself when I've seen this. Doesn't it remind you of something like the languages with garbage collection have this overhead? And in fact, actually, reference counting is a form of garbage collection. Right, so what are the alternatives? Do we have any alternatives, any ideas? So?
Don't use shared.
I love it. Yeah, the alternative would be actually, I just mentioned it, and this is what we use, is garbage collection. And you ask me, garbage collection, even in C++ and even in the performance talk, that sounds crazy, right? But let's look at this. So in Chrome, in Blink, in the rendering engine in Chrome, we actually have garbage collection. This is used because we have like V8 heap, the JavaScript heap, and we have the DOM heap, C++ heap. And in V8, we have garbage collector, and it must trace all this, also the C++ objects. It's all considered the entire graph, the whole graph, the same graph. So yeah, this is a tracing garbage collector. It implements the most famous, I guess, algorithm called mark sweep. Marking is basically the phase when you traverse the object graph, and sweeping is the reclamation phase when you traverse the heap and destroy all the objects that are dead. Right. So, and what characterizes OilPan, the garbage collector, is that both of the phases are concurrent to the main thread, to the application. So there is single synchronization phase, very tiny, but there is one, and this one can be performed actually when the browser is idle, when the user reads an article or whatsoever. So yeah, this garbage collector can also compact backend stores of containers, which can reduce memory fragmentation, right? In theory, in practice, we don't often see this, but it's a different story. Yeah, so API of the garbage collector is actually somewhat trivial. So you need to inherit from the garbage collected class. Whenever you construct object, you need to call cppgc make garbage collected. It allocates the object on the managed heap. It's basically the counterpart of make shared. For the pointer abstractions, we have members. So this is like shared PTR basically in the managed world. And we also need to provide the trace method, basically the method for the GC to know how to trace the object. It cannot be auto-generated with C++. We don't have meta classes yet. Yeah, but what is good for us is that we have a clang plugin which warns whenever you forget to trace something. It will warn that you need to provide a trace call for this specific member, because otherwise it would be unsafe, right? Because if you miss the trace call, it may result in a dangling pointer, and it may result in use after freeze, and there is no use after freeze in the managed world, right? And we don't have it in OilPan. Right, so let's look at what characterizes this garbage collector. The allocation is blazingly fast. It's based on the bump pointer allocation strategy. Whenever you allocate an object, it just bumps the pointer, right? You can think of it as a monotonic buffer resource from C++17. The allocation path is fully inlined. This is different from malloc, which is usually like a PLT-directed call across shared libraries. Right, and size class computation also happens at compile time, so that compiler can do more constant folding. Yeah, and it's single-threaded by design, so no synchronization of thread caching involved. So marking, as I've mentioned, is concurrent, and sweeping is also concurrent. And what characterizes sweeping is that it knows the concrete type of the object to be destroyed. So we don't have a need to have virtual distractors because we have our own, like our TTI, right? Runtime type information. So yeah, so the question becomes what to choose: reference counting versus garbage collection. And this is a tricky question. So if you look at the pros of garbage collection, what we have is fast allocation, no leaks due to reference cycles, no use after freeze security issues, and this is really, really important for Chrome. No log prefixed instructions, so barriers in the hot path, and no op distractors, of course. There are, of course, cons. For example, we have higher CPU usage, and which results in more power consumption, right? Because we need to do some work like traversing the object graph, which we don't do in unmanaged world. We have usually with garbage collectors, we have higher memory overhead because like we are lazy with GC. And there is also a cost of the write barrier. So the write barrier is a primitive that is executed when GC is in progress on each pointer, right? It's yeah, however, it happens like 1% of the time, so it's really rare. And one of the main drawback is just it's unfamiliar to C++ developers. So it's hard for people to choose from malloc allocated objects to OilPan. The question is what to choose. Is the question actually boils down to what is being optimized. If we optimize performance, like if we consider performance as responsiveness of the application and latency, yeah, then probably garbage collection can give something because we don't spend time on reference counting, so we can be faster, and allocation can be faster. But when it comes to CPU utilization and power, I don't know. Like, yeah, it's probably garbage collection is not a good idea because like you would have to execute a lot of code that you wouldn't in the unmanaged world. Right, so we decided to run an experiment. Actually, I decided it like not a long time ago, a couple of weeks ago. We take the same highly allocated class hierarchy, which we just flattened before, like this, yeah, the very same class hierarchy, and we move it to the managed world. So this is the flame graph of the frame that allocates a lot of such objects. It's not really necessary to know what is inside those boxes. This is what it used to be in the malloc world, and this is what it has become. Like literally, it has become 3.5x faster, and it resulted in 0.7% speedometer score improvement. I was surprised myself that the allocation is so blazingly fast. I believe this is the main reason we have fast hot path of allocation. We have better object locality due to the bump pointer strategy. And the slow path is also extremely fast. We have fewer page faults. Actually, what you see here is just like going to the kernel. So all of those are page faults. These are the slow paths of allocation. And we have just a single one here. And this is because in free list based allocators, like for example, malloc allocators, often use. In 3D based allocation, whenever the allocator allocates the super page, which consists of multiple system pages, it needs to iterate. It needs to initialize the free list in all of those pages. So it basically must eagerly commit all those system pages, and that can be expensive. Of course, we can use like madvice to commit them within a single round trip to the kernel. And this is what partition alloc actually does, but still it's expensive. And we also have page pool in OilPan, which makes it the slow path faster. Yeah, the next question is what else to profile. So if you look at the bottom-up view, we will see functions like memcpi, memmove, and memcmp. Of course, we all know that like compiler generates call to these functions whenever it needs to, for example, initialize with 0 things, or like no, actually not initialize, but like to move things, trivially copyable things, for example. Right. So, and if we expand, for example, the memcmp call, we will see that 30% of the 30% of all the cycles are actually taken by string comparison in V8. And string comparison in V8 is actually very simple. We have 2 pointers to string objects on the V8 heap. We take buffers from those objects, and then we call memcmp on those buffers. And we were always taught to never optimize memcmp and memcpi because it's already like well optimized inside the libc and so on. But never say never. And we decided to conduct an experiment. For this specific use case for string comparison, we unroll the loop or memcmp loop. We unroll it for small lengths, and this helps us to avoid the function call. We use SIMD for average lengths, and we fall back to memcmp for large lengths because memcmp can also do like optimizations for large lengths, like non-temporal loads of stores, which bypass the cache. Right, so this is what it looks like. Very simple. We take the power of 2 of the lengths, right? And for small lengths, we do like byte by byte comparison, or we can do also overlapping comparison of words or half words and so on. So it's really trivial. For average lengths, like from 17 to 1000, we do SIMD, the code exactly as usual with SIMD. Right, so it actually it's not really important what happens here. But for the two-fold case, yeah, we fall back to memcmp. Right, and the result was surprising, actually. We got 46% faster string comparison, which resulted in a 0.5% speedometer score improvement. I believe mostly the reason is just like avoiding the function call, avoiding the, yeah. Right, so yeah, a bit more on SIMD. There is a Canadian professor called Daniel Lemire. Daniel has a very good blog and writes a lot about SIMD things and tricks such as vectorized classification, which is used in the SIMD JSON library, also developed by Daniel. I believe this is the fastest JSON parsing library out there. Right, so there is also an optimization called call splitting. Actually, not optimization, but the pattern. It's basically when you always inline the hot path and outline the cold path. Like it's used in multiple places, like allocation, for example, vector expansion, a lot of different things. So the question is unlikely attribute for the cold path and the attribute no inline enough for the cold call? So we decided to look at somehow we looked at the generated code of, this is not a real code, but this is just for example. So this is basically vector expansion, and we have a vector of integer pairs, right? We push back into the vector, and if we run out of capacity, which is the cold path, we call expand capacity, which is no inline, and we want to keep it no inline so that whenever the compiler, so that we doesn't pollute the cache, the I cache with some other instructions, right? And in the hot path, we just insert this thing into insert the integer pair into the backend store. And on the right side, you can see the generated code. In the red rectangle, you see the hot path. In the blue rectangle, you see the, sorry, in the blue rectangle, you see the cold path, and in the red one, the hot one. And actually, if you look closer at the generated code, I'm not sure if all of you can see it, but if you look closer, there is an interesting effect. There is something the compiler does, clang does, and this is some register speeding, register reshuffling. Yeah, if we look closer, actually, it's not needed for the hot path at all. It's totally unnecessary. Right. For the hot path, hot path can avoid it. It can operate with all the registers it has. But I assume what happens is that the compiler doesn't recognize that this is a hot path, and it doesn't even do it with PGO. It sees this function, that the function is not leaf, so it decides to save the volatile registers to the preserved registers, because it knows that the expand capacity call can clobber those registers. So this is tricky. And this function is called like from multiple places. This is actually, well, not this function, but similar functions like vectors functions. They are called from multiple places, and they're really hot one, and they are always inlined, right? So we always inline. We try to always inline the hot paths. So why does the compiler do this? This is still open question. We tried using cold hot function attributes. So there are these attributes to let the compiler know that this is a hot thing and this is a cold thing. It doesn't help at all. It doesn't have any effect on the generated code. And I forgot to mention that unlikely actually only does is just reorders the it just reorders the basic blocks. It just only affects the placement of the basic blocks. Right. So cold hot function attributes don't help at all. I tried to switch the clang's register allocator, didn't help either. And then one of my colleagues came up with a brilliant idea. What if we change the calling convention? So there is this extension, LLVM extension, LLVM attribute, which is also available in clang, called preserve MOS. This actually entirely switches the calling convention, and it makes the, if you mark a function with this attribute, this function must preserve all the state that it has when it's being called. So it does help. And if you look at what the code becomes, the hot path has become like almost 40% shorter than it used to be when we mark the function with when we change the calling convention of the function. This is really great. So we tried this attribute in multiple places, and it resulted in 2% performance improvement on the WebAssembly compilation. We also got faster allocation and the write barrier path in the garbage collector. Yeah, and it also resulted in binary size improvement, in code size improvement, just because these allocations, these hot paths are inlined everywhere, right, in the code. So that's great. And the issue is that there is no 32-bit support for this calling convention. It doesn't work with built-in directed calls with calls across shared libraries, because at least the glibc's dynamic linker is not aware of this calling convention. Maybe in other dynamic linkers it works, I don't know. So we don't enable it on non-static builds. And it used to be broken in Clang, in some relatively old versions of Clang, and I actually had to fix it there. Right. So let's talk about compiler switches. Basic block placement. This is an interesting thing. We actually enabled a new PGO-based basic block placement, the basic block placement that relies on profile-guided feedback. And this is actually also developed by Facebook. It was initially developed for Bolt, and it's used by Bolt, but they upstreamed it to LLVM. So yeah, it's based on the extended traveling salesman problem. I don't know all the details, but it happens to work really great. So yeah, we have better iCache, ITLB utilization. If we run the code through perf, we see that we have fewer ITLB misses. right? And it resulted in 1% speedometer 2 improvement on Linux, which is great. Right, we also use relative vtable ABI. I'm not sure how many of you have heard of it. This is different from the default Itanium C++ ABI, but it differs only in the virtual tables. So the virtual tables, they consist of pointers right to the functions. And whenever you start your program, your dynamic linker must perform relocation. So it must assign actual addresses to the entries in the virtual tables. And this actually takes a lot of time. And for the project like Chrome, which is like giant project, it can take a lot of time. Yeah, and there is this ABI that was developed, I guess, developed by Fuchsia folks. The Fuchsia is the operating system developed here at Google. Yeah, so basically the idea is that instead of having pointers, we can use offsets, 32-bit offsets. Yeah, and it results in a faster startup just because we don't need to perform all those relocations for virtual functions. And it was a binary size reduction. So we enabled it on Android 64-bit, and on Android, the size of all the virtual tables was 7 megabytes. Like that's a whole lot. It's only virtual tables, right? And the binary size shrunk just by 2 because we have, instead of full pointers, we have offsets. Of course, it makes the cost of virtual functions slightly more expensive. Yeah, but we actually don't see this overhead a lot because like virtual functions, we don't use them in hot paths. We try not to use those. Right, so it's also enabled by default on Fuchsia. I think, yeah, if you compile your application with clang on Fuchsia, yeah, it will use this ABI by default. That's pretty much it from me. I would say I can talk about a lot of other different optimizations, but I would probably just save time for questions.
Thank you. So questions? No, I'm not surprised.
Thanks. 2 questions. First of all, do you inline assembly code? So back in my days when I was doing computer graphics, we would do all these optimizations, and then we would go to the small places and hand roll the assembly directly there because we would beat the compiler. Do you do these kind of things nowadays, or the compiler is always better than you?
We think that the compiler is always better. Actually, having inline assembly can impair optimizations because like on the IR level, on the middle level optimization, the clang and LLVM is not aware of what this inline piece of assembly does. It doesn't disassemble your assembly into IR level, so it can be tricky for optimization. So it can actually do poor job. What we actually use in V8 is we use built-in assume attribute. I think that this was standardized in C++23. Yeah, built-in assume, I guess it's called. It's basically gives a hint to the optimizer to do something. Yeah, but right.
And second question, which back to what I said in my talk, like you talk about this optimization at low level, but is there any architectural optimization that would drop the thing? So you said that string comparison is very costly. Mm-hmm. So you look at a DOM, maybe you're comparing object by ID, which is a string in your HTML code. And maybe you could just like, I don't know, hash all of this, and now you're doing integer comparison. So are you studying only like once the code is compiled, I'm trying to optimize this thing, versus no, I'm going to look at the architecture in my system and realize, I am done in the way. So
we actually have it. I have also slides about it, about like string, exactly that case when we canonicalize and deduplicate strings and just do a simple thing comparison of the pointers. It's also expensive actually. Like if just. Yeah, so this is the parser code. So we have a call to atomic string table add. This is basically the hash set that contains all the strings. And when in the parser we see like 1% of the cycles, they are taken by inserting something into this hash table. And this is expensive. We do did application for white space strings. White space strings is basically like string containing like spaces, new lines, and so on. And we need to parse those strings in DOM because of the DOM specification. This is just the text, and we need to parse it. And the DOM can be like, for example, here we have like multiple indentation lines and so on. So we try to save memory, and this optimization has been around for quite a while in all the browsers. But yeah, this just expensive. This is like crazy expensive because the algorithm, the existing algorithm was like, we parse the token. If the token contains white space strings, we try to canonicalize it. We compute the string hash, which actually involves another string, another pass over the string. And then we put it into a thread safe hash set, which involves acquiring the mutex. And then we possibly can also rehash the tables, which is another allocation. So this turned out to be quite expensive in the parser code. It's just 1% of cycles. Right. So yeah, and we did another optimization. We just like basically hot path extraction. We are based on observation that most of the HTML white space strings have the form like basically indentation strings. So we pre-initialize the n such strings in a static table, and whenever we parse such a string, we know, okay, this is like indentation. We off size, I don't know, 4, and it's basically single lookup, no allocation, no acquiring the mutex involved. So it's, and this table fits in the cache quite well. So yeah, we do such architecture. We do have such more macro architectural optimizations as well. I hope it answers your question.
It wasn't the setup. Other questions? Yeah, let me find the optimal. Yeah, exactly.
Thanks. I was wondering, do you have tooling or a good way to look at LLVM optimization reports? Because one thing I noticed for when I'm trying to look at how LLVM IR gets compiled properly is that by the time I'm looking at a properly optimized like release binary, lots of things get inlined. So I can't make much sense even of the basic blocks because everything is smeared all across the all across the binary. So anything is this optimization report is really verbose. So I was wondering, like, do you have?
Are you talking about the OptView tool,
right?
Or the OptView tool, or like AirPass or compile time?
Yeah.
Right?
Do you use that?
No, unfortunately not. I tried it. Like I only tried it myself. I generated the HTML report using OptView. I looked at some things like, for example, we don't use a strict aliasing. Like we pass no strict alias because we try to be on the safe side. And this is actually different from Safari. If I remember correctly, they use F strict aliasing. And it's broken in multiple places. In probably all the large projects that I've worked on, strict aliasing is broken. So I looked at the cases where like extra loads happen due to aliasing assumptions, and in the OptView tool, but it was just a single case. And I agree with you that it would be probably really useful to have an automated way to look at the missing optimizations and the optimization report by the compiler.
Right. Yeah, because I noticed just generally breaking auto-vectorization of loops is very easy. Like once you have the early exit diverging branch or something.
Right. What I found out like with the clang and LLVM, actually, I'm not sure if it has changed, but like 3 years ago, I looked at it, and the state of loop vectorization was not really that great, because whenever you have a control flow, I think that vectorization doesn't happen. The compiler cannot do it. Right.
I just have one more question. Do you use this portable SIMD stuff? I think Google has this Highway.
Highway, yeah.
Do you use it in Chrome?
Not in Chrome yet. Yeah, I like the author of the library contacted me to use it in on some another project actually. Right, but that project didn't ship, so we don't use the Highway. Yeah, so it's all the SIMD I showed, it was like handwritten, and it's there. Yeah, thanks for the questions.
Any other? Oh, yeah, traveling salesman.
You can pass it, I guess, to the people.
The mic. Yeah. See, optimization.
Thank you. I have two questions, actually. One is less on the profiling itself, but you mentioned things like variant, etc., resulting in uglier and more difficult to maintain code. And that kind of stuck with me because I do have these discussions about modern C++ features at work quite a lot. Do you think with more experience that opinion and view might change a lot? Things like StudVisit just becoming part of our identity?
Right, that's a good question, and nice T-shirt, by the way. Yeah, that's a good one. I think that C++23 doesn't have std overload, right? And without std overload, you would have to write like generic lambda with if const per things, like if const per, I don't know, std is same as like this type. So this is like really ugly in my opinion. Yeah, you have to like dispatch across different types, and it's not extendable at all. I don't know how to make it better, to be honest. I don't know, like, I don't know if it can get better, yeah, with programmers' experience, to be honest. Yeah, at least STD overloads shall be standardized. I don't know why it's not yet.
Okay, thank you. And the second one is about profiling tooling. Have you tried causal profiling, like COS, things like that? I think it's developed by the Institute of Emery Berger, where it will artificially modify the duration of some code paths and thereby identifying the impact of those code paths on your application.
What is it called, sorry?
COS, C-O-Z.
No, I
Okay,
haven't, but it's developed by Emery Berger, you mentioned, right?
Yes.
Oh, nice. No, I haven't heard of it. We only use this symbolizer thing, I guess it's called. Well, not symbolizer, stabilizer, exactly. Right, because we do see a lot of impact of like code layout changes. It tends to be better with PGO, but not always.
Okay. Yeah, I've tried it a few years ago. It wasn't very mature, but he presented it again at CPPCon this year, and so maybe it's worth a shot.
Nice, thanks for mentioning it. Yeah.
Thank you. So my question is, all your optimizations lean towards trading space, right? For speed or for ease of access. Do we have to expect Chrome to need a separate partition at some point?
Separate partition, I mean, in terms of memory?
No, in terms of disk space. And also, do you measure the load time of the binary? Like if you load a 100 megabyte binary, it takes a second. Not a literal second, but takes more time than a 1 megabyte binary. Is that a concern you have already, or are you still in this area where like SSDs are fast enough and it will just load? If we give it a 500 megabyte binary, it's fine.
I think, yeah, we try to optimize it as much as we can. For example, we don't load it multiple times for different processes. We have a single process that we just like Zygote process that forks itself and saves some time. I'm not sure, to be honest, how to answer your question. I'm not sure I even know. Yeah.
Okay, so you're still growing to gain speed.
You mean in terms of binary size?
Everything and memory footprint and.
I don't think so. Like I implemented optimization like last year for example, in the garbage collector we have now pointer compression. So our pointers are actually not 8 bytes in size in 60-bit world, but it's like 4 bytes in size. The gain was like 4% memory footprint improvement. That's not a whole lot, but it's actually not bad.
Not bad, yeah.
So we optimize in different spaces, not only performance. Performance was like one of the main objectives for us this year, but memory is still something important. Yeah, pointer compression was shipped in the oil pan garbage collector. We have pointer compression for B8 objects, for the JavaScript objects, so which actually also gave even more benefit in terms of memory. So yeah, and surprisingly enough, it's not always you have to find a trade-off. Sometimes it can be you optimize memory, right, and your locality improves at the same time, so your speed improves as well. So we're looking into different dimensions.
Mm.
And binary size as well. Binary size is also important on Android, for example.
Mm-hmm.
Right.
Cool. Thanks.
Yeah. I hope it answered your question.
Thank you, Anton, for a great talk.